This isn't just poetry, it's a cipher. It is a surprisingly dense, technically accurate roadmap of advanced materials science.
A roadmap.
Yeah. It covers everything from basic alloy synthesis to uh, high entropy materials, hydrogen storage, even theoretical self-healing structures.
It's like someone took a graduate-level materials science textbook and just compressed it into verse.
That is a perfect description, and frankly, it's refreshing. It sort of strips away all the jargon and just leaves you with the raw concepts.
So that's our mission today. We are going to decode this thing. We're going to take this chemical quest, as the poem calls it, and unpack the actual hard science hidden in lines about, ternary amalgams and thinking metals.
And we should be clear, the stakes here are actually pretty high. This isn't just about making a shinier car bumper. If the tech described in these verses is accurate, as we'll see it largely is, we are talking about the fundamental materials that will enable the energy transition, space exploration, and the next generation of computing.
Okay, let's get into it then. The poem opens with a stanza that feels a bit like a chef staring at a pantry. It says, "In a chemical quest for the best, try this or that and the rest." It sounds so casual.
It does sound casual, but it's actually a nod to the history of the field. For, thousands of years, metallurgy was basically alchemy. It was all trial and error. Try this and that.
The poke it and see what happens era of science.
Exactly. Throw some arsenic into copper, see what happens. Oops, everyone got sick. Okay, try tin instead.
Right. But then it immediately shifts gears to the modern era with the next couplet. It says, "Perhaps concoct a multi-element blend that will more than satisfy your end."
And then it drops the hammer with this next line. Its ordered atomic lattice configuration surpasses by a margin the defined intention.
Okay, ordered atomic lattice configuration. That's a mouthful. We need to break that down right now.
So imagine a pure metal, say pure iron. At the atomic level, it looks like a perfect stack of oranges in a grocery store. Perfectly neat, identical rows.
Okay, I'm with you.
And because those atoms are all identical and the rows are perfect, they can slide over each other really easily. That's why pure metals are usually soft. You can bend pure gold with your hands.
Which is great for jewelry, but terrible for building a bridge.
Precisely. So when the poem talks about a multi-element blend, it's talking about alloying. You take that stack of oranges and you shove a grapefruit in there. Or maybe a lime. You introduce a different atom.
And suddenly the rows can't slide anymore.
You've put a speed bump in the atomic highway. You've distorted that neat lattice. That's the ordered atomic lattice configuration it's talking about.
And what about that line, "surpasses by a margin the defined intention"?
That's the key. It's synergy.
Meaning the whole is greater than the sum of its parts.
Much greater. You add just 1% carbon to iron, a tiny pinch of dust, really, and you don't just get slightly harder iron, you get steel.
Right.
A material with completely different properties that literally transforms civilization. You are surpassing the intention of the individual elements.
The poem then highlights two specific properties, ductility and conductivity, and it credits a specific mechanism. Aluminum bonds engage to chemically embrace. Now, embrace is a very poetic word for a chemical bond.
It is.
But is there a reason it singles out aluminum?
There is. Aluminum is sort of the social butterfly of the periodic table. It has this incredible ability to form solid solutions, to embrace a huge variety of other elements without wrecking the metallic structure. It's incredibly versatile.
It's the friendly neighbor in the lattice.
It is. And it allows for lightweighting while keeping that conductive path for electrons. That's why it's the backbone of aerospace and the electrical grid. The poem is acknowledging that aluminum is often the embrace holding it all together.
Okay, so we're mixing atoms to stop them from sliding. Now, the poem gets more specific. It drops the phrase ternary amalgam.
Right.
Now, my Latin is a bit rusty, but ternary just means three, correct?
It's a three-part mixture.
And the text places these in gears and contacts interlace. I found that really interesting. Why 3 elements for a gear? Why not just 2? What's the third one actually doing?
It's solving what you could call the Goldilocks problem.
Yeah.
In engineering, you rarely need just one property.
Okay.
Take a gear, it needs to be hard so it doesn't wear down.
Sure.
But if you make it too hard, it becomes brittle. They'll just snap under shock. So you need toughness too. Or an electrical contact, it needs to conduct electricity like copper, but not rest like copper.
Yeah.
And be hard enough to be switched on and off a million times.
So with just 2 things, you're usually stuck with a trade-off.
Exactly. You optimize for hardness, you might lose conductivity. A ternary amalgam lets you triangulate. Use one element for the main body, one for strength, and then a third to maybe stop corrosion or add some kind of lubrication. You're balancing the variables.
Speaking of specific combinations, the next section introduces a really kind of mysterious one. It talks about electronic sensors in some gadget's core.
Yeah.
And then it tells us to dig out that palladium-mercury amalgam once more.
Yeah, that once more is what caught my eye.
It sounds nostalgic, like something we used to use and stopped, and now we need it again. And mercury. Isn't that, persona non grata in modern electronics? We spent decades trying to get it out of things.
You did, and for good reason. But material science is cyclical. Palladium-mercury is a very specific system. Palladium is incredible for sensing, specifically for detecting hydrogen gas.
Ah, okay, so it's sensor.
It absorbs hydrogen like a sponge, which changes its electrical resistance. But when you form an amalgam with mercury, you tweak its electronic structure. You change how sensitive it is, or what it reacts to. The poem suggesting we dig it out once more implies a comeback.
But why now?
My guess. The hydrogen economy? We're going to need incredibly sensitive sensors to detect leaks everywhere. So we might be returning to these older, more complex, maybe slightly dangerous recipes because they offer a precision that modern silicon just can't match.
So it's a case of old tech, new problem.
Exactly. Sometimes the solution to a future problem is in a Victorian chemistry book.
All right, let's shift from delicate sensors to brute force. The poem takes us into extreme environments. It introduces high-entropy, multi-element alloys.
The HEAs.
Yes, this is a buzzword I've been hearing a lot. High entropy. Now, to most of us, entropy just means chaos, disorder.
And in thermodynamics, that's exactly what it means. But here, that chaos is the secret weapon.
How does chaos make something stronger? That seems counterintuitive.
Okay, think about traditional alloys again. They're like soup, mostly broth. The base metal, iron maybe with a little spice thrown in. High entropy alloys are different. They're more like a fruit salad.
A fruit salad.
You mix 5 or 6 elements in roughly equal amounts. Cobalt, chromium, iron, nickel, manganese, you name it, all in there together.
So there's no base metal, it's just a mashup.
No base. It's a chaotic mix. And you'd think nature would hate that. You'd think the atoms would separate like oil and water. But if you choose the right elements, that high entropy, that high disorder, actually stabilizes the whole mixture. The atoms are so confused they just lock into place.
They get confused into stability. I love that. And what's the payoff? The poem claims they reflect strength and toughness at cryogenic rates.
That is the killer app for these things. Usually when you freeze a metal to deep space temperatures, cryogenic, it gets brittle. It shatters like glass.
The old liquid nitrogen on a rose trick.
Exactly that. But because HEAs has such a distorted, complex, sluggish atomic lattice, they don't lose their toughness. They can function near absolute zero.
But the poem immediately flips the script. It contrasts this with extreme heat. It says they also wear resistant coats to make turbines and structural components glow.
And glow means extreme heat. We're talking jet engines, gas turbines.
So wait, we have a material that survives the freezing vacuum of space in the inside of a combustion chamber?
That is extremely rare. And that is what the poem means when it says mechanical and thermal properties keep apace in energy tooling and aerospace.
So the engineering has outpaced the materials, and these alloys are finally letting us catch up.
That's been the story for the last decade in aerospace. We can design engines on a computer that burn hotter and more efficiently than any metal we have can actually withstand. We've just been waiting for the metal to catch up. HEAs are that answer.
Speaking of things we want to burn cleanly, let's talk about the energy section. This was a part of the poem that felt most like a patent application to me.
It gets very specific.
Very. It pivots to the hydrogen economy. It mentions metallic hydrogen materials and claims they enable much storage by reversing hydrogen uptake.
This is hitting on the single biggest problem with hydrogen power. Density. Hydrogen is a gas. It's the lightest element. To store enough to drive a car 300 miles, you have to compress it to insane pressures.
Which means heavy, expensive carbon fiber tanks. And I imagine people get a little nervous driving with that under their seat.
There's a perception issue, yes. But solid-state storage, these metal hydrides, they change the game completely. Imagine a metal that's like a sponge.
A sponge for atoms.
A literal sponge for hydrogen atoms. They don't sit in a tank. They chemically bond inside the gaps of the metal lattice. You can actually store more hydrogen in a cubic foot of this metal than you can in a cubic foot of pure liquid hydrogen.
That is completely counterintuitive.
It is, but it's true. The metal packs in tighter, And to get it out, the reversing uptake part, you just heat the metal up a little and it releases the gas.
But the poem gets very specific. It warns about cracking. Why would the metal crack?
Think about that sponge again. When a dry sponge absorbs water, it expands, right?
Right.
Same thing happens here. When the hydrogen wedges itself in, the metal lattice expands. If you do that over and over, fill the metal fatigues, it literally pulverizes, turns to dust.
But the poem gives us a recipe. It says, alloying magnesium with nickel or tin elevates, the absorption of hydrogen and cracking mitigates.
And that is a legitimate, real-world formula. Magnesium is the champion at holding hydrogen, but it holds it too tightly and it cracks easily.
So what do the nickel and tin do?
They're the catalyst and the stabilizer. Nickel speeds up the reaction. It's like a doorman, letting hydrogen in and out faster. And tin helps structure the lattice so it can expand and contract without shattering. The poem is literally giving you the formula.
And the promise here is massive. The poem says, hydrogen vaults breathe energy clean and vast, feeding grids no longer chained to fossil past.
Vaults breathe. It's a great image, isn't it? It's not a static tank, it's a breathing battery. This is the tech that lets you store solar power from the day and release it at night to run a fuel cell.
It's fascinating. The barrier to a green future isn't just politics anymore. It's whether we can mix magnesium and nickel correctly in a factory.
Material science is almost always the invisible bottleneck. You can't legislate your way around physics. You have to engineer through it.
Okay, we've done solids, we've done gas sponges. Now the poem gets fluid. It introduces eutectic amalgams that flow at room temperature like mercury.
Eutectic's a fun concept. It breaks all the rules. You take two solids, say gallium and indium, and when you touch them together at room temperature, they just melt into a liquid. The mixture's melting point is lower than either ingredient.
That looks like magic, like the T-1000 from the movies.
It looks exactly like that, but the application it highlights is specific to make thermally conductive interfaces glow.
So we're talking about cooling electronics.
Right. Your CPU gets hot. You need to get that heat to the fan. We usually use thermal paste, that gray goop, but paste is mediocre.
And air is a terrible conductor.
Terrible. And on a micro level, surfaces are rough, like mountain ranges. If you put two metals together, they only touch at the peaks. A liquid metal flows into every single microscopic crack. It creates a perfect thermal bridge.
So as our chips get hotter and faster, these liquid metals are what will keep them from melting down.
Exactly. It lets us push the hardware harder.
This leads us into the final stanzas, where things go from industrial to visionary. The text starts talking about latticed codes where quantum states align, and smart alloys that function by engineered design.
Yeah, we're crossing a line here from passive materials to active ones. Lattice codes implies the information isn't in a silicon chip attached to the metal. The information is in the structure of the metal itself.
Programmable matter.
In a sense. And it gives us this wild example. Self-healing grains mend fractures out of sight through nanothreads that weave by day and night.
Mend fractures out of sight. I mean, that stops me in my tracks. We're talking about metal that heals itself like skin.
That is the ultimate goal. Imagine an airplane wing. It gets a tiny microfracture from fatigue. Today, that's a catastrophe waiting to happen unless the mechanic finds it.
But with this stuff.
The material feels the stress, the crack alters the local energy. The nanothreads, maybe they're shape memory alloy fibers or little capsules of liquid metal, they activate. They pull the crack closed, or they rupture and flow into the crack to seal it.
And this just happens automatically.
That's the smart part. It's a physical reaction. It heals by day and night, meaning it's a continuous passive system.
The poem culminates with adaptive skins on crafts, and the phrase that really stuck with me, thinking metals guard each structural core.
Thinking metals. It really challenges our definition of intelligence, doesn't it?
How so?
We think intelligence needs a brain, a CPU. But if a material can sense its environment, process that data by changing its physical state, and then act on it by healing itself, it's performing a computational loop. It is, in a way, thinking.
Distributed intelligence. The wall of the spaceship isn't just a shield, it's a guardian.
It's the difference between a castle wall made of dead stone and a line of soldiers who can link their shields and move. One is static, the other is responsive.
That really reframes the whole chemical quest we started with. We're not just looking for harder rocks, we're trying to wake matter up.
That's a beautiful way to put it. Waking matter up. That is essentially the frontier where nanotechnology and metallurgy are meeting.
Wow. Well, for a rhyming PDF, Amalgams Galore definitely delivered. We went from basic aluminum bonding all the way to sentient, self-healing starships.
It's a good reminder. You can have all the AI you want, but at the end of the day, civilization is built on stuff. Atoms, lattices, amalgams. If you can't master the material, you can't build the future.
So